everyone. Welcome to our second session of I/O Day. Before we get started, I wanted to ask, how many of you have a NERSC training account? Okay, how many of you have used it? All right, so if you want to use the burst buffer on Cori at NERSC, you're going to need to use either your regular NERSC account or a training account. The burst buffer is available to everyone. If you're going to use the training account, then I'd suggest you use our compute reservation. I have a reservation of 100 or so Haswell nodes for the training accounts. So this means if you want to run something on Cori on the Haswell nodes using your training account, you should be able to get almost immediate access to the nodes rather than waiting around in the queue. This is something we set up for the training day for today. The node should be available until around midnight tonight. And so if you wanted to do some testing and running in the evening, then that's available for you as well. Otherwise, you have to take your chances with the queues. So the material that I'll be presenting, I think you all have access to it. You can also find this in various other burst buffer type materials from burstbuffer.org. That will take you to this site. You can then click through to the website for this particular tutorial, which has the slides that I'll be presenting. And these are the slides that are on the workshop website, so you're not missing out by looking at those slides. Okay, so what I'm going to be talking to you guys about is basically contradicting all the things that you've just heard in the first session. So you've just been hearing about how you really want to be doing nice, coalesced, large read-writes in your HPC code. And the burst buffer is a technology that's designed to mitigate all the problems associated with that kind of I/O pattern. And I'll go through in a bit what I mean by that, but I'm really focusing in this talk on some of the kind of issues that you might have if you have a non-standard HPC type code that might be doing a lot of small reads, small writes, high IOPS types I/O patterns, and how you can use the burst buffer and this kind of technology to make that a less painful experience. So as I haven't been here for the rest of the week, have you had an introduction to the NERSC systems yet? No? Okay, so I'm not going to go into any detail about this, but I just want to point out that the memory hierarchy at the moment is heading towards a more fragmented model. So we talk a lot about memory hierarchy in the kind of meetings that I go to. And this basically means, where are you putting your storage? And so in the olden days, Edison, for example, is our workhorse supercomputer. It came on the floor in 2013. Has a fairly standard memory hierarchy. You have off-chip storage, large amount of storage. That's our project and Scratch file systems on the spinning disk. And then we have on-chip memory very close to the CPU. On Cori, we made the design decision to try to improve the I/O experience of our users by splitting this up. So off-chip, we have, again, the large capacity fast storage on the spinning disk. We've inserted a layer of what we think of as near storage on SSDs, and this is the burst buffer that I'm going to be talking about in more detail. And then actually on the chip, we have two types of memory, the far memory, DRAM, and near memory, high bandwidth memory. I'm not going to be talking at all about the on-chip memory. I'm going to be focusing entirely on the SSDs, the burst buffer technology that we have in Cori. And the reason why we make this decision, the reason why we make these kinds of design choices, is really to enable faster and more efficient data movement. That's the whole point of all of this. We want to try to bring everything closer to the cores so that you have more efficient access to the data from your program, from your application. And this is, from our point of view at NERSC, this is to enable what we consider to be data-intensive computing, to address the volume and velocity issues around scientific big data. So I realize that this is something that most of you are perfectly well aware of, but I want to emphasize that there are mechanical limitations in spinning disk. And before I went into working at NERSC and really working with HPC, this is something I hadn't quite grasped. Like thinking about how your disk drives actually function. When you have spinning disk, you have to actually spin the disk to get to the location where your data is sitting. So you're always going to have latency whenever you're working with spinning disk. You're always going to have problems doing lots of uncoalesced random reads and writes to disk, especially if you have a large distributed parallel file system, which is what we tend to have at HPC centers. So SSDs are a very desirable technology to sit in place of hard drives because you don't have these physical drive components. So your read writes are always going to be faster, and the kind of random I/O patterns that a lot of codes, a lot of applications need are always going to be faster and better suited to SSDs. The problem is that SSDs are still very expensive. If we could afford to replace all of our hard drives with SSDs, then we would have done that. But although the costs are coming down, we're still not at a point where that's financially viable. So another issue with SSDs, which is something that the manufacturers are really working hard on, is that you have a limited write capacity. SSDs wear out. The memory cells wear out after time, and so if you have data-intensive type workloads, as we do at NERSC, then this is something that we actually are very concerned about, whether we're going to be able to maintain the performance and maintain the capacity in banks of SSDs. And so these are the two sort of areas, the expense and the wear factors that have gone into the decisions we made when we decided to purchase a burst buffer bank of SSDs for Cori rather than going down one of the other design choices that we could have done. So bearing that in mind, that we can't replace all our spinning disks with SSDs, what are we going to motivate our use for a burst buffer for SSDs? How are we going to make the most use of this? How are we going to leverage the technology? And the classic motivation for the burst buffer, the clue's in the name. It's to buffer bursty I/O patterns. This is the original sort of design plan behind the way the various burst buffer products have been developed. And it really is just a design to handle spikes in I/O bandwidth requirements. This is obviously a good thing. If you have the type of traditional HPC application that we were talking about this morning that has has checkpoint restarts capabilities or are writing out large volumes of data, then you will have your application that's running along quite happily and then have a sudden burst of I/O as you write out the checkpoint file. And if your code is structured so that you have to wait while that I/O is happening before you can start compute again, then you could be wasting a lot of your time in I/O. So if we can handle these kinds of spikes in I/O, then we're going to reduce application runtime for our users. That's important. I don't know if you're aware of how this, you're probably aware of how this works, but at NERSC and as other HPC centers, we have very little control over the amount of hours, compute hours, allocated to our users. They are given an amount of compute by their DOE program managers, and they have to spend that compute as efficiently as they can. So anything we can do to reduce application runtime, anything we can do to improve I/O bandwidth is going to be very welcome to our users. But it's not just, of course, about getting our users good performance. It's also about us. We want to see our compute resources used efficiently. We don't want to see these big spikes of I/O going to our file system because that can overwhelm the network. We can have knock-on effects if we have really large amounts of I/O, and especially if it's metadata-heavy I/O going to our file systems. That can cause problems on the system side as well if you have a very I/O-intensive application. And so from our point of view, we want to be able to handle this kind of workload in a more efficient way, as well as free up all our compute cycles to be used for actual compute rather than hanging around for the I/O. So that's sort of the classic motivation for a burst buffer. And this is what actual grabs of I/O to our Lustre file system from the 2nd of February earlier this year. And you can see that we really do genuinely have spiky I/O in our systems. This is read and then write. And you really do see big spikes of I/O in our systems. And if we have a lot of these kinds of spikes, then things can start to fall over. That's not the only reason why we want to have this kind of technology in place. At NERSC, we have something like 6,000 to 7,000 users on our systems. Of those, probably 3,000 to 4,000 are very active users of our systems. And that's a lot. We have over 700 different projects that run, which means we have over 700 different code bases that run on our machines. And so we have a great range of codes that run and a great range of science problems that are run. Not all of them run in the traditional HPC type model where you're doing a large amount of compute-intensive simulation, writing out checkpoint files, writing out large data files. We have a significant number of user applications that have what we think of as challenging I/O patterns. And these are, high IOPS, random reads, when you have different applications that are trying to access the same files at different concurrencies, very tightly coupled workflows, these kinds of things. Those are the kinds of I/O patterns that just don't do well on spinning disk. So it's perfect to move these kinds of I/O workloads onto SSDs. And this is why, this is from our point of view, why a burst buffer is a useful thing on our systems, because we're able to fix some of these I/O problems. And I mentioned before that SSDs are expensive. Disk capacity is quite cheap. SSD bandwidth is quite cheap. And so the design decision that we made when we were designing Cori was to try to separate those so we can offer this burst buffer that gives high bandwidth performance but doesn't have the same capacity as our Scratch system. And I'll talk a bit more about later how we leverage the network speed within the supercomputer itself. So Cori is our newest supercomputer, number 6 on the top 500 list at the moment. It's a Cray XC40. You all have access to it. You should feel free to log on and check it out. Cori is slightly unusual in the sense that we have two kind of partitions, two different types of compute nodes on the supercomputer, sitting in the same fabric, sitting in the same cabinets. There are a number of design reasons behind this I can tell you about later if you're interested. But we have something like 2,400 Haswell nodes. These are 32-core, 128 gigabyte memory nodes. And then something like 9,700 Knights Landing Xeon Phi nodes. Those have 68 cores and 92 gigabyte memory. If you want to know more about these, you can just Google NERSC Cori and you have all the stats come up. It's a Cray product, so we have the Cray Aries interconnect. The burst buffer sits inside that interconnect. I'll show you some pictures of that in a minute. Our file system is a Lustre file system. That's our Scratch file system. We have 27 petabytes, 248 OSTs for Scratch. At peak, when we did our benchmarking of our Scratch system, with a completely empty, when there were no files on it, when it was just delivered, and we had nothing else running on the compute nodes, we could get 700 gigabytes per second peak performance. And I make all those caveats because today the best possible performance you could get out of it is probably closer to 300 gigabytes per second, because we're at something like 65% capacity on Scratch, and it's much harder to get peak performance out of a full file system, whereas it is not so difficult to get peak performance out of a burst buffer, even when it's highly occupied. So you have 28 petabytes of Lustre Scratch. We have 1.8 petabytes of burst buffer. So this is what the architecture of Cori looks like in a very simplified way. So we have compute nodes. We have the I/O nodes that were mentioned just earlier this morning. And also within the high-speed network, within the fabric of the interconnect, we have burst buffer nodes. So the burst buffer deliberately placed within the high-speed network to leverage the network speed, to leverage the connection speed between the CPUs and the SSDs. Just to give an overview of how people actually see this, how people use this, We have the data warp product from Cray. So this means that the SSDs are controlled through the data warp software. This is something that's very well integrated with our workload manager. We use Slurm at NERSC, and data warp integrates very nicely with Slurm. And this software allocates portions of the available storage on the SSDs to users when they request it. This can be on a per job basis, so you can request an allocation on the burst buffer while you're running your compute job, or you can request a persistent allocation, something that's going to persist for longer than your single compute job. The thing that's nice about this is that when the user has their job hitting the compute nodes, there is a POSIX file system mounted for them on those compute nodes that has been constructed by the data warp software by carving out portions of space on the SSDs in our burst buffer pool. And so this means that this file system can be striped over multiple burst buffer nodes, depending on how much space you've requested. And by striping the data, by striping the file system over burst buffer nodes, you can aggregate the available bandwidth from each burst buffer node. I've got a little bit more detail of how that works later on, but this means that in principle, if you have a burst buffer allocation that's striped over every single burst buffer node, you can get the maximum possible performance out of the burst buffer, which can be over a terabyte per second bandwidth. Yeah, question?
How do those Intel SSDs compare to something that a user would buy off the shelf?
Okay, so what's my next slide? So this is what it actually looks like. Okay, so the SSDs that we've bought, I think the main difference compared to what you get off the shelf, this is high capacity. We have 3.2 terabyte SSDs, 2 per burst buffer node, so total of 6.4 terabyte SSDs. And granted, today you can buy terabyte-size SSDs, but to have the reliability that we've required in our SSDs costs more. So we have very high-end SSDs. And the big factor in the choices we made in purchasing these is that we have strict requirements on the wear. So I mentioned before, SSDs wear out if you have too many writes. And so there's a pretty sophisticated system on the SSD itself that is checking which areas are being written to and moves the writing load around the SSD so as to not to wear out any of the memory cells too much. So that's somewhat complicated. It's a complicated system. I can't pretend that I understand how it works. But basically, we have, on each SSD, we over-provision the SSD by 20%, so that there's 20% empty capacity at all times, and that's deliberately chosen in order to be able to have the flexibility to spread out the writes on the SSD cards themselves.
Some of these units break. Can you replace them easily? Or are they like soldered?
Can we replace the SSDs easily? In principle, yes. In practice, we have not done so. I think we have one SSD that failed so far out of the 500 odd SSDs that we have, and that was that failed during the integration and test period. So we haven't actually had to do that yet. But yes, in principle, they can be swapped out, yeah. So this is what the blade looks like. So this is, I should show you, this is, if you open up a cabinet in Cori, you see all these blades in the cabinet. These are compute nodes, and this is in each cabinet, there's a couple of burst buffer blades. And that's what it looks like. And if you pull those blades out, which I don't recommend you do, then this is what it looks like. So you have the Aries interconnect chip here. You have 2 drivers here, Xeon CPUs, and then the SSDs here. So each blade has 2 burst buffer nodes sitting on it. Any other questions about the technology before I move on? Okay. So as I said, we've got 1.8 petabytes of SSDs over 288 nodes. It's accessible from both of our compute nodes, from Haswell and KNL. So the reservation we have today is on Haswell nodes. You can access the burst buffer from those. You can access the burst buffer from KNL nodes as well, if you wanted to take your chances with the queue for KNL. So we're not the only site to have SSDs. Argonne has SSDs. Plenty of other labs have SSDs in their supercomputers. The way that we've configured our SSDs, the way we've configured our burst buffer is slightly different. So we've chosen to not have node local SSDs. So this means we don't have an SSD plugged in the back of every compute node, as is the case at some sites. And there's a few reasons for that. One is that that would have been very expensive to plug an SSD in the back of all, whatever it is, 13,000 compute nodes that we have. It would have been a lot. But the other reason is that that kind of use pattern for SSDs doesn't really fit our workload at NERSC. Because I mentioned before, we have a diverse workload. We have thousands of users, hundreds of different codes that run. And at any one time, there's probably 1,000 or more jobs running on Cori. And so we have a lot of jobs that are very I/O intensive, but not compute intensive. And so if you wanted to take advantage of SSD bandwidth and a job that only requires 10 compute nodes, you'd only have access to 10 SSDs. And you might want to have access to 100 SSDs. And so that means you'd have to configure your job, if you're I/O bound, to waste a lot of compute time. And that's just obviously inefficient for everybody. So that was the main motivation behind why we've chosen to have this pool of SSDs in a configurable burst buffer that any user can request an allocation of. And there's a couple of other sort of more edge use cases. We work with a number of experimental facilities who want to do real-time data analysis. And for that, they want to stream their data into the burst buffer and do their analysis in real time. So they're streaming the data directly into the burst buffer. That's very hard to do if you're trying to access an SSD that's on a compute node. If you have a separate pool of SSDs, then it's much easier to configure that kind of thing. And also having a pool of SSDs, a pool of burst buffer, means that you can have these persistent reservations without having a persistent reservation of compute nodes that might be sitting idle and unused while you're not actually using the data. So for all these reasons, we chose to have a configurable burst buffer, and it's working out very well for our user load. So data warp under the hood. I'm not going to go into a great deal of detail about what data warp's doing. In the backup slides, I have a bunch of much more detailed slides about how the striping is done within data warp. And if there's interest, I can go over those later. But they're in the backup slides. So basically, how does this work from a user's point of view? Well, you request a job to our workload manager, to Slurm, requesting an allocation on the burst buffer. Slurm schedules the job in the queue on Cori and simultaneously goes and talks to the data warp service to say, hey, this job, this user is requesting an allocation of the burst buffer. So the data warp service goes and carves out however much space has been requested from the burst buffer pool, configures this, and mounts this space onto the compute nodes when the compute nodes are allocated for the job, when the job's ready to run. Another feature of data warp, something that I actually really like, is that you can stage your data in and out of the burst buffer before and after your compute job runs. And this is something that is handled by data warp as well. So data warp will, if you request in your allocation that you want this directory or that file staged into the burst buffer, then data warp will go ahead and do that for you, so that when your job hits the compute node, your data is already sitting there on the burst buffer in your allocation, ready for you to work with. And similarly, if you specify a file or a directory to stage out, then that will be taken care of after your job has finished executing on the compute node. So the really nice thing about this is that you're not wasting your compute time moving data in and out of the burst buffer. So again, we've got maximum efficiency of your compute nodes. So the way this actually works, data warp creates an XFS file system for each user, for each allocation, that's been put together from stripes of, or grains of burst buffer. So as a user, you see this XFS file system, a POSIX compliant file system mounted on your compute nodes when you're ready to run.
I have a question.
Yeah.
The data warp service come with the SSDs, or is it something that was written in-house?
So Data Warp is a Cray product. We bought that from Cray, and we have Intel SSDs. Now, you could have any SSDs in there, but you'd have to talk to your Cray rep about how you configure that. But it's a Cray product, and I'll talk a little bit later on about how we've been working with Cray to make sure that everything is working well for us. Yeah.
Is there any control how the digital space is actually allocated? For example, how many burst buffers you're actually going to be allocating on?
So the question there is, does the user have control over how the burst buffer space is allocated? Not much. So in principle, I actually have a bit more about this in a couple slides, but very little control. That's something that is a feature that we've requested. So there's going to be some progress there, but it's not straightforward. The administrator has total control over how burst buffer allocation is created. So if you want to have an allocation that has definitely striped over every single burst buffer node, then you talk to your system administrator and they set it up for you. Other questions before I move on? Okay, so I'm going to cover some jargon now because there's a lot of data warp and burst buffer specific jargon. And the reason why I want to talk about the jargon is because it's the when you're using the data warp control API, these are the terms that are used, and they're not always that intuitive. So an instance on the burst buffer is your allocation. So there's these two different types of instances, one that is created for the duration of your job. This is known as a scratch instance. So it's created when your job is submitted, and it's torn down when your job finishes. And at the end, you don't need to remove the data from your allocation at the end of your job. It will be all deleted for you. And so that also saves you some time in your compute job. So this is the typical use case for this is really checkpoint restart as well. I mean, you can use this for anything, but it's very efficient for checkpoint restart use cases because you can just have this allocation that's running throughout your job, write out your checkpoints, you get to your next checkpoint point, you just write out the next checkpoint to the same place, and then at the end of the job, whatever remaining checkpoint file is there gets written out. So it's a pretty efficient way of using this for checkpoint restart. If you have a persistent instance, which we also call a persistent reservation or a persistent allocation, this is obviously a longer running allocation. The lifetime is controlled by the creator, so you choose when you want to destroy, that's the terminology, destroy the allocation. And it can be used by any job. So we have a lot of users that have these kinds of persistent instances where they are working in a group and they have their data, their experimental data staged into a persistent allocation, and then there's multiple users running, accessing that data and analyzing that data. So that's a really useful way of a group being able to take advantage of burst buffer bandwidth. And it's also really useful if you have a coupled workflow. So if you have a simulation job that's writing out data and you want to have a simultaneously running analysis job that's analyzing that data, and then perhaps a third job that's doing some visualization of that same data, you need a persistent allocation for this. You can't access this through a Scratch type instance. I emphasize this is not intended for long-term storage of data. We only have 1.8 petabytes. And so we do, at NERSC, we do try to enforce that people don't keep their data on the burst buffer for too long. That's partly to free up space for all the users, but also partly because SSDs do fail. It does happen, and perhaps more often than the SSDs failing, the software, the node software gets corrupted, and we have to reboot, and we might lose or corrupt data. So that's something that you have to bear in mind. You have to sort of balance these things. If you're choosing to use SSDs for your data, bear in mind that it's not guaranteed, it's not backed up. Yes?
Question about per job instance and checkpoints. We do checkpoints in case of failures, right?
Yes.
If we have a failure, our application crashes and all the nodes go down. So we lose the checkpoint in that moment.
right?
Well, not necessarily. Okay, so if you have a job that is running quite happily, writing out its checkpoint files, then the job crashes, the compute nodes crash, the burst buffer nodes don't necessarily crash. Now,
For instance, because it's per job.
not necessarily. If you have specified that you are staging out a file or a directory at the end of your job, and the data on the burst buffer is not corrupted, or even if it is corrupted, but that data that you specify to be staged out is still sitting on the burst buffer and can still be staged out at the end of the job. So it depends, though, on how badly your code crashes. If it crashes so badly that it brings down the burst buffer nodes, then you're probably not going to get access to that data. But it is, if you have, if you run out of wall clock time, for example, then the data is still on the burst buffer and it will still be staged out at the end of the job, whatever it is that you specify to be staged out. Now, the downside of that is you need to know in advance what you're going to stage out, which I'll go through in the examples later. But
Just to use the persistent instance.
that is safer, yes. Yeah. Yes.
I apologize if you already answered this, maybe and I missed it, but can you do funky stuff where you have a persistent instance and then you have another, and say one job creates a persistent instance and then says, okay, I'm done, and then you have another job that you want to access that persistent instance. But can that second job have like a per job instance, or is it only?
Yeah, you can absolutely have persistent and per job instances in the same job. And in fact, I think you can have several Scratch, we call them Scratch instances, several Scratch and several persistent instances accessible to a compute job at the same time. Yeah.
So I'm confused. I thought that burst buffer meant that it was like a cache in between the file system, but you're saying that you could store explicitly on there?
So the way that we use the burst buffer is not as a cache necessarily. We leave it up to the user to do what they want with it. Now, in the Data Warp product, there is a phase of functionality called transparent caching. And in that functionality, which is not yet available, hoping it'll be available soon, Data Warp can be used as a transparent cache between the parallel file system and the compute. And so in that sense, that's the sense that you're meaning. So it depends on the site, it depends on the system. There are sites that use the SSDs, use a burst buffer as a cache, as you say, and you can use our burst buffer in that way, but you have to configure it to do that yourself. Yeah, that's a design choice that we made. We like having the flexibility, so you can use the SSDs as a sort of temporary storage layer as well. Yeah.
If you have a persistent instance and you want multiple jobs to access the data, do the different jobs have to be running on like the same cabinet that the burst buffer's in, or
yeah, so that's an interesting question. So no, the burst buffer node scattered throughout the fabric of the supercomputer, and any compute node can access any burst buffer node. And so you can have compute jobs that are completely independent, and as long as you've set the permissions, the POSIX permissions correctly, any job, any user can access that burst buffer persistent allocation. You can have several jobs running at the same time. Now, the issue with that, of course, if you have several jobs running at the same time, accessing the same data files, you want to be really careful you're not going to step on each other. You're not going to be overwriting each other's files. That's something that we sometimes see coming up. But that's the same no matter what kind of file system you're using. No other questions? Okay. So then let's talk about the access modes. So there's two different types of access modes, striped, also known as shared, and private. So when you are running in striped mode, as the name suggests, your files are striped over all Data Warp nodes, and the files are visible to all compute nodes in the job. So this is, if you have multiple compute nodes that are all accessing the same byte of data, then this is the mode that you want to be using. The data is striped and the access is shared across a compute node. A key point to this is that you are aggregating both the capacity and bandwidth per file, so that you have access to the aggregate bandwidth of all the burst buffer nodes in your job for every compute node. But something to bear in mind is that we have one Data Warp node that's elected as the metadata server. in this node. So you have one metadata server for the whole allocation. The big difference between shared and private mode is in private mode, files are visible only to the compute node that created them. So it's like having a SSD/temp available. So each compute node has private access to whatever data it's writing. No other compute nodes can see that data. But it's something that can be a real advantage in this mode is that each data warp node is a metadata server for one or more compute nodes. So you can leverage this if you have a large allocation striped over many burst buffer nodes. You have a really high capacity metadata server available to you. And I've got an example later on about how you can really take advantage of that. So any questions about this functionality? Okay. Other bits of jargon. You've been hearing about striping earlier today. We also have striping. We have your files. If you have more than one burst buffer node in your allocation, and you choose to have your data striped, then data will be striped over burst buffer nodes in 8 megabyte stripe sizes, substripes, and there's several other layers underneath there that the data warp service software does. In addition, striping over the individual SSDs, it gets very complicated. But the thing to bear in mind is 8 megabytes. Stripe and a multiple of 8 megabytes, and you'll probably be okay. But there's this other terminology we have of granularity. So burst buffer nodes are configured to have granularity. That's configured on our side, on the system side. And this is the minimum amount of data that's going to land on each node. So in Cori, at the moment, we have two different pools of burst buffer allocation. One is the default node, pool, which we call the WLM mode for the workload manager pool. The granularity here is 82 gigabytes. So if you requested an allocation in this pool of 80 gigabytes, your data would all sit on one node. If you requested an allocation of 85 gigabytes, this would be striped over two nodes, two burst buffer nodes. And this is the biggest performance tip I can give you. If you want to be able to take advantage of the aggregate bandwidth of multiple burst buffer nodes, then you want to have your data striped over multiple burst buffer nodes. So over request your allocation. Over request the amount of space you need when you're thinking about the kind of bandwidth you're going to want. We also have another pool that we call the small pool, SM pool. This is something you have to explicitly request. This has a granularity of 20 gigabytes. This is for users that don't require very much capacity, but want to be able to take advantage of the aggregate bandwidth. So for example, if you request 1.2 terabytes of allocation in the WLM pool, this will be striped over 15 burst buffer nodes, but in the small pool, it'll be striped over 60 burst buffer nodes. And I should mention that the theoretical maximum bandwidth from each burst buffer node is something like 6.5 gigabytes per second. So in principle, if you request 60 burst buffer nodes, then you'll get 60 times 6.5 gigabytes per second bandwidth available to you, depending on how you're doing it. I should point out that, as with the question earlier, there's no guarantee that your allocation will be spread evenly over the SSDs. You can't at the moment guarantee that you'll get one grain on each burst buffer node. So you may find that you have multiple grains on the same node, which will reduce your bandwidth, your effective bandwidth. Okay, so at the moment, the way that the data warp product is configured at NERSC is that you can only do I/O from the burst buffer to the parallel file system, so to our Lustre file system. If you have multiple burst buffer nodes in your allocation, then the I/O to and from the parallel file system will be done in parallel. And compute nodes are not necessarily involved in this I/O if you're doing data staging in and out. And so I'm going to go through some images here from Glenn Lockwood at NERSC, who made these really nice images sort of demonstrating this. So when you're requesting your job, when you submit your job, you request some allocation size and whether you want to stage data in or out. And these are kind of the data paths. You have the burst buffer nodes that sit inside the high-speed network. You have these I/O nodes which go to the parallel file system. So you note that there's this connection through this path through the compute nodes and directly through the I/O nodes. So if you want to stage data in before the job starts, then data goes directly from Lustre through the I/O nodes to the burst buffer nodes. Compute nodes are not involved. At job runtime, then the compute nodes are reading back and forward from the burst buffer nodes, again, not using the I/O nodes in this case, just going straight forward through the high-speed interconnect. Something that is not efficient is if during your job you decide to copy data from the parallel file system to the burst buffer. This is not an efficient way of doing this because the compute node issues the copy command. It goes through the I/O nodes to the parallel file system, pulls the data through the compute nodes to the burst buffer node. So this is an inefficient way of moving data around. I suggest to avoid it if possible because it can be remarkably slow copying data from Lustre to the burst buffer during a compute job involving a compute node. The best way really is to use the stage in and stage out capabilities. So let's see, I've got 20 or so minutes left. I'm going to spend about 10 minutes now going through a couple of use cases that demonstrates how performance is good on the burst buffer. And then I'm going to very quickly go through the hands-on demonstration, because obviously we're not going to have time to go through that in detail now. But I want to at least talk you through the commands that you will use, you can use to access a burst buffer. And if you want to look at the other slide deck that's part of this, and that goes through the commands in some more detail. But the basics is that you can access the burst buffer and control access to the burst buffer almost entirely through your Slurm job submission script. Very straightforward. You can use this to allocate a per job or persistent instance to stage your data in and out. It's very straightforward. And then the burst buffer mount point is defined by environmental variables depending on what type of allocation you've requested. So I'll go through this in more detail in a bit. There is also an API, a libdatawarp API that you can, it's in C, so you can compile that into your code and control in more fine detail the access, the movement of data to and from the burst buffer. I'm not going to go through that in any detail because, frankly, it's less well developed than the Slurm interface, and it's much easier to use the Slurm interface. So burst buffer, we probably have the best performing I/O system in the world. In our benchmarking, we have up to 1.6, 1.7 terabytes per second bandwidth, which is pretty nice. And that's in POSIX file per process, slightly lower in MPIO, shared file benchmarks. But something that I really like is our IOPS benchmarks. We are able to get something around 28 million I/O operations per second, which is fantastic for the kind of workloads we have at NERSC. And I should mention that we significantly outperform Scratch at this point for nearly all I/O patterns. So I mentioned a little bit earlier that we use burst buffer for coupling workflows, and this is kind of our poster child of an example that couples a simulation, analysis, and visualization code together using the burst buffer to enable science to be done at a resolution that wasn't possible before. So this is a code called Chombo Crunch. It's a code it's basically a geophysics code. It simulates different ground layers and the transports of liquid and gas through the ground layers, and it's used for carbon sequestration simulations. And the key point here is that if you want to have a higher resolution simulation, you have more accurate science. If you want a higher resolution simulation, you have much larger data files that you need to output. And this can be a real problem when you're trying to do I/O to spinning disk. If you're trying to write out 100 terabyte files to our Scratch system, you're going to have something of a bottleneck there. So the burst buffer allows this kind of simulation code to go to the higher resolution, higher accuracy simulations without spending 90% of their time in I/O, which I think is roughly where they were before. So that in itself is pretty neat, but also by using a persistent allocation on the burst buffer, they could simultaneously run the analysis and visualization code. so that they can do that in a really efficient way, and they can just get to their science more quickly. Before, they'd have to run their simulation, write the output files to Lustre, and then in a separate job later on, subsequently do the analysis, and the whole process took a lot longer. So I want to point out the scaling of this. So this was one of our first use cases for the burst buffer, and it's very similar to the checkpoint restart type use case that burst buffers are designed for. Because it's writing out large quantities of data. It's not a high IOPS random read-write application. And the burst buffer significantly outperformed Lustre at all scales. So that's all scales of running with different numbers of compute nodes and with different size data files. There was no additional tuning required, just out of the box. They were getting something like 4 to 5 times faster I/O to the burst buffer than to Lustre. And this is pretty typical. We're normally seeing something like 4 to 5 time improvement in I/O for this kind of use case. We've got large reads. Some more, from my point of view, more interesting use cases are the ones that are IOPS heavy and have random reads and writes, because those are the ones that are most challenging on Lustre, as we were hearing earlier this morning. So this is a comparison of performance on our Lustre Scratch system and the burst buffer for an analysis code, a data analysis code from the ATLAS collaboration, which is one of the particle physics experiments running at the Large Hadron Collider. They have these really large analysis files, something like 50 terabytes worth of analysis files. And their analysis code is combing through these files, pulling out specific events that are of interest. So they're kind of doing a filtering process, pulling out specific events and doing more detailed analysis on those events. This is very IOPS heavy. There's lots of random reads. And in this use case, they found that the I/O was something like 9 times faster on the burst buffer compared to Scratch, which was really nice. And I'll point out here as well, something that was mentioned earlier on is this variability in your I/O, depending on the system load and depending on just how the bandwidth, how the network is doing today, if it's having a good day or a bad day. You see this variability is huge, these enormous error bars here. There's, well, uncertainties here. There's a lot of variation. Even on the burst buffer, you see this is not negligible, the variation in bandwidth that you get from the burst buffer, and that's largely down to the network, to how our interconnect is behaving today. So another success story is from the JGI. This is the Joint Genome Institute, which is one of the institutes at Berkeley Lab. They have a lot of codes that are very data intensive, very IOPS intensive, because they're doing genome assembly. And there's a specific code, a meta-genome assembly algorithm, that has a tremendous amount of small random reads and writes. I/O is a significant bottleneck for them. And they've been spending a lot of time tuning the striping, tuning the performance on Lustre. And they thought, well, after all this work, let's just try the burst buffer and see how that goes. And they got an immediate factor of 2 improvement in their I/O without doing any tuning at all. And that's something like a factor of 10 improvement compared to their original performance on Lustre. And so something that I particularly like about this is that I had nothing to do with this. We had an early user program where we were working very closely with people who had I/O problems in their code to try to get them up and running on the burst buffer. And we're at a point now where anyone can just use the burst buffer and it just works for them. And it took a significant amount of work to get there. When we first got the data warp, it was a new product, and it hadn't been tested very much under these kinds of workloads. And we broke it almost every week, finding new corner cases, new use cases that the burst buffer either couldn't handle or couldn't handle efficiently. And so we're now at the point, after working very closely with the very, very smart Cray engineers, we're at a point where we have very good performance for basically everybody. I'm going to skip through the next few slides because I've been taking a really long time to talk through my slides. If you want to look at this in more detail, this is a detailed use case of a high IOPS SQLite benchmark. It's basically very small transactions in a database. This is some work done by Chris Daly at NERSC. I'm really looking into the details of what takes the time. The key point here is running this benchmark on Scratch and on the burst buffer. It's something like 50 times faster to run on the burst buffer than on Scratch. And this is sort of the platonic ideal of an IOPS-heavy workload. It really is something that just works on SSDs in a way that it doesn't on spinning disk. So I'll leave you to look through the system commands for this. Okay, so to summarize, we've got a really nice burst buffer. You get good performance out of it. Typically, users see 4 to 5 times improvement in I/O, up to 10 times, maybe up to 50 times if you have a particularly awful I/O pattern. And you are welcome to try this out. Anyone who has a NERSC account can access the burst buffer on Cori.